Hi everyone, my name is Brooke, I'm a geologist, and today is really exciting because we're here at Charwood Forrest to look at the Bradgate Formation, which is Ediacaran and contains some of the oldest large possible animal fossils in the world. It's about 560 million years old. I'm here with the students from Oxford, so let's go and have a look at some really cool rocks, find out what the Ediacarans were and what they're up to. I'm so excited because I've wanted to come here since I was a little kid, and this is like, oh, dream come true.
Geology is really cool. Let's go lick some rocks. Yeah! Here we see the young earth scientists listening to Ross talk about these fascinating sediments we're about to investigate. The rocks, of course, have no idea what's about to happen, but the young earth scientists will thoroughly geologize them. Isn't nature beautiful?
So two things that make the rocks of Charwood Forest so special is the fact that they record the transition from the Precambrian into the Cambrian, and so the Cambrian marks the start of the Phanerozoic, where you get large fossils, but also they have these Ediacaran fossils in them, and those are large body fossils of organisms that lived before the rise of all of the animals that we would recognise today. But before we look at any fossils, we need to find out if we're looking in the right kind of rocks. We need sedimentary rocks. So we're going to look at these rocks and see if we can find any features that help us identify if they're sedimentary, metamorphic or igneous. You've probably already noticed actually that they're full of lots of layers and they have a grainy granular texture, and those features usually indicate that you're dealing with a sedimentary rock. We've also got this feature here where it looks like something's poked its way through the sediment layers, and this is something we call a way up structure because it literally tells us which way is up. If you look closely, you can see that the layers bend downwards as though they're filling in some kind of hole, so it's like something poked its way up towards the top of the screen and then all of the layers slumped downwards. And in this case that was probably water. We can see we've got all of these fine layers and they're mostly made of sand grains, so that sand was probably building up on the seabed really quickly on the edge of a slope, and because you can't compress water, as soon as you start to build up too many layers in the sediment, the water erupts upwards. So because of that, we know that this flat surface here where my hand is actually the primary bedding. That's the old sea level, but this other surface that's at 45 degrees is something else entirely. These surfaces aligned at 45 degrees are actually faults and cracks caused when the rock was buried and then uplifted and tilted. So these are a tectonic feature and not a primary bedding feature. We can see we've got this brittle fracture, so we know that the rock had been solid for millions of years when it was broken. It's pretty cool to know that you're running your hand over what used to be the seabed 560 million years ago, back when the UK was near the South Pole. So cool! Oh. But why was all the sediment building up so fast on the seabed? Well, there's actually a big clue in this rock here. See if you can see what it is as we look round. You probably noticed this green-grey block in amongst all of the sandstone. So what have we got here? This is a piece of mudstone. You can tell because the grains are too small to see. They're even smaller than sand grains. And it's made of something different to our sand because it's got this green-grey colour. And that's because of a clay mineral called chlorite. And that means that this probably started off with a lot of volcanic material in it, and that it's been buried to a great depth and it started to metamorphose into what we call a green schist. Whenever you see big ragged square chunks like this in a sediment, you know there's been a high energy event. And volcanic eruptions are pretty high energy. So because of this, we know that these sediments were probably deposited on the side of a volcanic island, and that bits of rock and sediment and the sea floor every now and then would come crashing down the side and build up in these big piles along the base, just like happens on modern volcanic islands today. Oh dear. We've moved on to a different location now. We're next to Bradgate House and we're looking at this rock here. We've got a very different kind of rock now because this isn't a sediment, but it's still just as old as still Ediacaran. Typical. The helicopter comes over when I try and talk. This is quite clearly a very different rock. For a start, we've got all these pink crystals here, and this is an igneous mineral called orthoclase, which is a type of potassium-rich feldspar. We've also got these spaces where this greasy grey mineral is weathering out because it's much stronger than the surrounding material, and that greasy grey mineral is quartz. You can see it's missing all over. We've also got these little tabular pale white crystals that you can just make out, and that's another feldspar. This one's called plagioclase. This combination and proportion of quartz and two types of feldspars tells us that we've got a volcano that was probably erupting above a subduction zone where one plate is sliding under another and you're having development of an island arc, and that kind of goes along with the story we've seen of the sediments further down the hill. The fact that we can see these big chunky crystals means that this rock cools deep under the earth, so this is probably part of the magma reservoir that was feeding the volcanoes that were erupting and depositing our sediments. These linear features are called slicken sides, and they're something that formed long after this rock had solidified. They're caused by rocks sliding over each other in repeated earthquakes, so this is probably related to the deformation as the rock was uplifted and tilted like we saw in the sediments down the hill. So we've come along from Bradgate House now, and we're at a little quarry, and what we've got is this big blocky rock here that you can see in the B-roll, and it's got these grains in it, so it's got granular rock and it's a sediment. But which way up is it? Because as you see from the B-roll, it's a bit of a mess. So what I've found are these lines, and these lines represent old sedimentary structures. We've got crossbedding, we've got lamination here, and then a crossbed that goes along there. And what I've done is I've made a sketch of it. There we go, this is what we should be seeing. We can see as well we've got graded bedding. So we've got these coarser quartz grains here, and then moves upwards into finer grain stuff. We've got our slicken sides as well over there. So these are all sat on top of our Ediacaran deep water sediments, so these are going to be much younger. And we actually know that these are Cambrian, earliest Cambrian sediments, and this would have been sandy shore face, so a beach or just offshore of the beach. We've got some cool tectonic features here as well. These gashes are where the rock has been stretched, and that's called an N-echelon tension gash array. So the rock has been stretched and then dissolved quartz is crystallized and filled inside it. And they're really cool. Sure sign that you've had tectonic activity, and you can see that they're cutting across our original bedding, so this definitely came later. And lastly, we can see here, there's the line of the old bedding. See our quartz grains have all been cemented by more quartz. There's another crossbed there. And what this is a vug. So this is a space where something's dissolved out of the rock and then mineral grains have crystallized inside it. And like an iceberg, most of that's going to be buried under the sediment surface which goes along there. So that tells us that this way is down and this way is up. And that lines up with our observation of the primary sedimentary bedding, which was getting finer upwards because coarse grains settle first. So that way was paleo up, and our beds, that direction is paleo up. So our beds have been turned almost vertical. Now we've moved on to the next locality, and we've gone back in time to the Ediacaran sediments. What we've got here is called a turbidite sequence. You can see these bands. So these are deposited by underwater avalanches, and we know that because we've got these sudden coarse bands and then these fine bands in between, and they get weathered out. Of course, a trip to Charwood wouldn't be complete without seeing the famous Ediacaran fossils, and there's one right there. That weird feathery looking thing. These things were living on the seafloor about 560 million years ago, and then they were suddenly buried by either volcanic eruptions or one of those underwater turbidite landslides. These circular structures are holdfasts, so this is what's left of where the animal was attached to the seabed. So here's our last location for the day. This is Bomb Rocks, and these are weird volcanic rocks that were deposited around the same time as the Ediacaran fossils are being deposited. Let's go and have a look close up and see why they're called bomb rocks. When a volcano erupts, a big gobbet of lava, and it twirls through the air and gets an aerodynamic shape, then we call that a bomb. And you can see that these rocks have all of these nice big rounded blobs in them. When we look at them closely, they're full of igneous minerals like those feldspars that we saw earlier. So people assumed that they were volcanic bombs, but that's not probably the case. They're definitely igneous, and they were definitely formed while they were still gooey and hot. But they also look a lot like a conglomerate or a breccia, which are sedimentary rocks that are formed when big chunks are broken up. So what we think's happened here is that this is a lava flow flowing downhill, and it's cooling and breaking up and then eroding itself as it goes to produce this conglomeratic, brecciated lava mixture. It's really cool and really unique, but it's something you see on modern volcanic islands today. When we look close up at this bomb, we can see that we've got all of these nice pink potassium feldspars and the white feldspars, and there's some quartz in there as well. So this is definitely an igneous rock, not a sedimentary rock, though it has been tilted like the sedimentary rocks that we saw earlier, and because it's got this bedding feature, we can work out which way is up, and we can work out that it's been tilted as well. Well, that's all for this trip. I hope you've enjoyed looking at these rocks from 550 million years ago. I've always wanted to come here, so I've been quite excited. It's been really great for me. Thanks very much for watching. Take care. See you later. Bye bye.